without, without further ado, we're going to go ahead and finish discussions about fluids. So, having finished fluid dynamics, now we're going to talk about fluid, or having finished fluid statics, now we're going to talk about fluid dynamics, which is what happens when fluids move. And it's a small but important part of fluids, and most of it is Bernoulli's principle. Now, you've all encountered Bernoulli's principle because you've been driving down the road, and when you open one window, you hear that bum, 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 bum noise, and it like kind of pulls in your ear.
Yeah.
That's because fluids, when they move, they exert reduced pressure.
Wait, Bernoulli trials and Bernoulli principle the same thing? Or, I mean, I know they're not, but like,
So you can?
Bernoulli, there's a thing called Bernoulli trials.
Never heard of it.
Stats,
I mean, it's entirely possible. I mean, back a couple hundred years ago, you were rarely limited to one discipline. But so, to fully understand, or at least partially understand, Bernoulli's principle and the thought process that went into it, you got to imagine gas at the molecular level. So, if we think of gas molecules at the molecular level in this balloon, what direction are the gas molecules in this balloon moving? Yeah, all of them. They're moving all the directions. So, since gas molecules in three dimensions are moving in every dimension in the x, y, and z plane, then we can basically say they average out to not be moving at all. We tend to like, oh, the gas molecules aren't moving at all. It's just right there. But we realize that they are, in fact, moving. In fact, they're moving extremely fast, almost as fast as the speed of sound in many cases. So they're moving really, really fast, but they average out to not moving. Okay, does that idea make sense?
Yeah.
Now, we also have to discuss what is pressure. Ultimately, at the molecular level, what is pressure?
Pressure.
What is it?
Pressure.
Where does it come from?
Pressure. Mexican food.
It comes from stress. I've turned so many things in. My parents have expectations.
Isn't it like a lot of air?
I had to bring honor to the ephemery.
You guys have to bring honor to your ephemery.
So
Yeah, at the molecular level, what is pressure? Where does it come from? It comes from air molecules, so nitrogen and oxygen and helium, whatever else is in there. But what are they doing? They're moving. And you encounter pressure when something moves and hits something. So pressure comes from molecular collisions. So what we really talk about when we say there's a lot of pressure is there's a lot of molecular collisions transferring a lot of momentum. Okay? So when we increase pressure, we're increasing the momentum of the gas molecules. Make sense? Okay, so back to our balloon. So our balloon has a sample of gas, a bunch of nitrogen and oxygen and water vapor and carbon dioxide in the balloon, and those molecules are moving in every direction. Okay, so far so good? Now, if I take my balloon and I move it like so, are they still moving in the same direction? Is the speed of the molecules the same?
Yes.
What's causing the balloon to move?
You're adding.
Yeah, I'm applying a force on the balloon, but the balloon has to do what? It has to change direction. Okay? So if I have pushed the balloon molecules this way, I notice that they apply a force back on my hand. I know, I can close my eyes and I know the balloon's still there because I can feel it applying a pressure or a force on my hand. Does that idea make sense?
Yeah.
I'm like, oh, that balloon's still there. Oh, the balloon's gone. Okay. So I know that it's applying a pressure back on my hand. So if some of those collisions are directed backwards, then what happens to the amount of momentum in every other direction? If some of the molecules, right now, direct the momentum of all the gas molecules in every direction, but if I make it so some of the gas molecules, more of them are pushing back, then fewer of them are pushing what other directions? All the other directions, exactly. So when gas molecules move, they exert less pressure in those other directions. So if you take a barrier and you blow air into it, then some more molecules are moving in one direction and less molecules are moving in the perpendicular direction. Does that idea make sense? Okay, so that's the basis for Bernoulli's principle. Simply states that when gases move, they exert lower pressure. Well, they don't really exert lower pressure, they just exert lower pressure perpendicular to their movement. So, I mean, you know this, if I was to you blow on your neighbor, you're going to exert more pressure on them. They're like, hey, there is more pressure. But, so this is partly why airplanes work and why helicopters work. So, airplanes have these foils. These are called airfoils, and they're fatter on top and smoother down below, smaller down below. So the air that goes over the foil has to take longer, or has to move faster to get over the wing. The air that moves under the foil moves slower. So the air over the foil that is moving faster exerts less pressure than the air moving under the foil, which moves slower. Okay. So above the wing, you have a higher velocity air. Higher velocity air exerts less pressure perpendicular to its movement, and that means it's producing less force. Under the wing, the velocity is smaller, so the amount of pressure that the air under the wing exerts is larger, so the amount of force under the wing is larger. That is the basis for how airplanes kind of work. Okay. It's not the only thing. It's actually a small part, but this is important. This concept is important. It would be incorrect to say this is the only thing that makes airplanes fly. What's the most important thing that makes airplanes fly? Angle of attack. It's literally called angle of attack. So when you put your hand out, you're driving down the road, and you tilt your hand forward, then the air pushes your hand up. So that's also important. Both things are important. Some things are more important for jetliners and helicopters than fighter planes. Yeah. Okay. Okay. This is also why sports cars have that crazy wing on the back. Yeah. Why do sports cars need that giant wing in the back?
It helps keep the back wheels on the ground and push them hard up the
Yeah. Most cars are not exactly a foil, but they're close. I mean, the general idea is when you're building a car, you want the car to cut as small a hole in the air as possible. But you have to fit people in there. So the car ends up looking kind of like this. This is a wing, and the air moving over the car exerts a less pressure than the air moving under the car. That's a problem, because what's the most important thing when you're driving a car? Staying where you want to be, staying on the ground. In fact, auto racers like NASCAR and Formula One, their engines can go a lot faster than the cars should go. Okay, so if they're going around 180 miles an hour, their engines can make the cars go faster. Why don't they go faster? No, not because of restrictor plates. Because they would lose what if they went too fast? They would lose control. They lose friction. So that's the most important thing. Auto racing is not about your engine. It's about your tires. It's about your suspension. It's about your friction. You want as much friction as possible. Well, here's the problem. When you're going really fast and air is going over your car, what is that reducing on your car? This is probably a little bit of an exotic idea. Remember this one? Remember this? Normal force. Now, if the car is stopped, then the Fg down is exactly countered by the normal force up, right? That's just like you. Your butt force is exactly countered by the chair's normal force. So the problem is when cars get going faster and faster, the amount of normal force is, well, part of it's due to the upward drag. Basically, the car's pulled forward. So to keep that from happening, or to reduce that, then you put a big fat wing in the back. So when the air hits the wing, it bounces. I guess the car is going this way, so my car is going to the left. So you put a big old wing right there, so that causes the air to bounce, which pushes the back of the car down. Yeah? Well, it doesn't leave the ground, so the downward weight and the upward forces are equal to each other. So it decreases the normal, or it increases the normal force by decreasing the drag. Does that make sense? So the overall force is different. So the normal force that creates friction gets reduced because there's drag pushing down. So reduced normal force means reduced friction, which means when you turn, not as much force can happen on the tires, and then you crash, and then you run into something. Yeah. So, by the way, just as an aside, does this help you at all if you put a big fat wing on the back of a Honda Civic? Not at all, because a Honda Civic is front-wheel drive, not rear-wheel drive. In fact, in extreme cases, if you put a wing on the back, you're going to push the back of the car down and the front of the car up. You're going to reduce your friction on the front car. Except you're actually just adding weight. So does it help? Yeah, it adds weight to your car. That's about all it does. If you have a rear-wheel car, then you might need a wing back there. Any questions? Yeah. Okay, so go tell your hoopty-doopty older brother that their wing, that big aluminum wing he put on the back of his Honda doesn't really do anything. Just adds weight. You can do the same thing by just throwing a brick in your trunk.
That's a lot easier and it looks cooler.
Yeah. Okay, so most of you have washed a car. If you take a hose and you turn on the hose and you put your thumb over the end of the hose, what happens to the water coming out? Yeah, it speeds up, okay? It speeds up, it leaves faster. Hoses are a little tricky in our analogy because there's a gigantic pump downtown that makes sure everybody gets about the same pressure in their house. That's why when your neighbors flush the toilet, the water pressure in your house doesn't change very much. Not that you can notice. So it's a little dicey, but in general, when you put when you block the hole and make the area coming out smaller, the water speeds up. That's called continuity. In other words, whatever fluid goes into a system comes out of a system. And this is usually the diagram that is represented as continuity. So fluids going in, fluids coming out. If we reduce the cross-sectional area, then the fluid has to move faster. So this is usually written A1, B1 equals A2, B2. A being the cross-sectional area of the pipes. So the area of the pipe and the velocity in the pipe equals the area of the new pipe and the velocity of the water in the new pipe, or the fluid in the new pipe. Now, what is the unit for area? This is not a trick question. Square meters, yeah. So area is square meters. And what's the unit for velocity? Meter per second. Yay, meter per second. So what unit do we have when we multiply A by B? What kind of meters per second? Cubed. Yeah. Meters squared times meters. So this, in other words, this is meters squared, and this is meters per second. So the unit we really have is cubic meters per second. In other words, volume of water in per second equals volume of water out per second. Okay? So if you put 1 cubic meter of water in one end every second, then hopefully every second 1 cubic meter of water comes out. So that means if you shrink the pipe, the water has to move faster through that shrunken pipe. It also means something interesting about diameters. We were just in the gym. Did you notice the ventilation system in the gym? The pipes are not all the same size. Yeah. As the air exits, the pipes get smaller. Okay. The idea is if you have less air, you need a smaller pipe to keep the overall pressure pretty much the same. So as air exits the pipe, you have to make the pipe smaller so the air can make it to the other end of the pipe. If you had one big long pipe of the exact same diameter, then all the air would end up at one end of the pipe, and it would all end up like blasting the freshmen, and the seniors and juniors wouldn't get any air. So, same thing, kind of like this. Only in that case, we're losing gas. But this basically means if we want to keep the pressure the same, if we're going to reduce the size of the pipe, the fluid's going to move faster. Okay. That's continuity. Questions? Only pitfall here is watch out for radiuses and diameters. Okay, make sure you're calculating area each time. If a diameter is given to you, convert it to area. If a radius is given to you, convert it to area. Okay. We'll get to that in a second. I'm going to skip over that and skip over that because we don't need it. Okay. We do need Bernoulli's equation. The rest of this stuff, not important. What we do need is Bernoulli's equation, which is cool. There was this guy named Daniel Bernoulli, for whom we named this formula. And it's a real trip of a formula. The formula works like this. Pressure at one state plus the changes in pressure, rho g delta H plus rho, or 1/2 rho delta V squared is a constant. Or you can say equals rho GH plus 1/2 rho V squared plus P. In other words, constant. The pressure at one instance is going to equal the pressure at another instance. That way, then we say P1, H1, V1, P2, H2, V2. Just like in the equation down there. Can't see the equation. Clicker. I don't mean to confuse you. Okay. So what is Bernoulli's equation? It simply states this. Absolute pressure plus any change to the pressure is going to be a constant. So what is rho? Yeah, it's the density of the fluid. Be it air or water or half-congealed jello, it's the density. What is H? Height. So pressure, rho, V is velocity, rho, gravity, height. What this means is, if you have a tube of water, and you pour water into the tube, and that tube runs down and then comes out here, the water is going to speed up as it falls. Just like a ball going down a ramp. You put a ball at the top of a ramp, what kind of energy does it have? Potential. You let go of it. It goes zoom. And by going down the ramp, it loses what? Potential, and it gains kinetic. Take a look at this formula. Look familiar? Rho GH. Doesn't that kind of look like mGH? And 1/2 rho V squared. Doesn't that kind of look like 1/2 mv squared? I'll prove it to you. It does. Because density is mass over volume. If you want to turn a fluid with its density into mass, you just divide by volume. In fact, there's something else. It turns out work, which is the change in energy, is equal to force times the distance. Remember that? What's this? Pressure is force over area. Volume is area times energy divided by volume is pressure. As I mentioned, right? Energy divided by volume. So basically, this is an analogy of if you take fluid divided by volume, you get energy. Pressure is analogous to energy. Pressure at depth is analogous to potential energy. And pressure due to moving fluids is analogous to kinetic energy. So just like a ball rolling down a ramp has potential energy and loses potential energy, turning into kinetic energy, when a fluid that's really high travels down a tube, it loses potential pressure, if you will, and speeds up. Does that idea make sense? Okay. If it makes sense, then we have a couple little discussions we talked about before. The hole. The hole. Here we go. Oh, before we do the hole, I have to mention, especially because it's going on YouTube, that we're totally ignoring all viscosity. Does anyone know what viscosity means?
It sounds very familiar. It's how well a fluid moves.
Okay. You want to develop that?
Yeah, isn't it like the thickness of the fluid and like how like ketchup and water have different
Yeah.
Viscosity.
How well a fluid moves, the thickness of water. It is the friction of fluids. Viscosity is the friction of fluids. And we're going to ignore viscosity just like we ignore air resistance. We're going to ignore viscosity because it makes the formulas not work anymore. So we're going to ignore it, just like we ignore air resistance.
Do we ignore that in physics AP?
Mm-hmm. Yeah, we totally do. Because it's a calculus thing. Remember how I said air resistance requires two variables to change on each side of an equation? Same thing with viscosity. Viscosity requires two variables to change on the other side of the equation. So that's the realm of calculus that we should decide. Okay, so here's the thing. Consider you have a drum 2 meters high. You got your drum about 2 meters high. It looks like about 3/4 of a meter wide. Big drum full of water. And you punch a hole in the bottom. How fast is the water going to come out? Pretty fast. How fast? We should totally do the math. In fact, I'd like you to do the math. So this is the equation you're going to use for Newton's principle. One side of the barrel is going to be condition 1, and one side of the barrel is going to be condition 2. You want to make this side 1 or 2? 1. Okay. So up here, this is going to be condition 1. Up here, or down here? Condition 2. So what's going to happen? Practically speaking, I mean, well, it's going to start emptying, right? Yeah. So it's going to go blah, blah, blah. So this is open to the environment, and that's important. It's open to the atmosphere. The atmosphere is going to push down on it, and it's going to force the water out. What's also pushing down on the fluid? Exactly, the weight of the fluid. So atmospheric pressure is going to push down, but also the weight of the fluid is going to push down on the fluid. And it's going to start emptying. And I'd like you to see if you can figure out how fast it's going to empty, or how fast the fluid is going to leave. Yeah, the water's all the way at the top. Now, obviously, you've seen this before. When the water starts going down, there's going to be less pressure. There's going to be less fluid on top, so it's going to flow out slower. But we're going to, at the initial, when someone punches the hole, then how fast it's going to flow. And again, if we ignore viscosity, we don't care how big the hole is. We're just going to keep it in very general terms. Sean?
Just out of curiosity, so when you tip something, it usually makes it flow about the same rate, right?
When you tip it?
Yeah, you tip it, and when it starts running out, you tip it, it keeps dumping at the same rate, doesn't it?
Not necessarily, because if you imagine if this is full and the hole's down here, if you tip it, now there's more gravity. There's more pressure because there's more gravity, there's more fluid. So that's usually why we tip things. So similarly, if I filled this up and I punched a hole right here, and I tip it this way, so there's more distance from here to here, then it's going to flow faster because there's more pressure.
Okay.
If I tip it this way, then there would be less because the height is only from here to here. Yeah. Remember, pressure is just rho gh.
Okay.
Gravity's not going to change, rho's not going to change, but the height of the column is going to change. Yeah. Okay, so how do you do this? Let's do this. Well, how might we start this exercise? There's a few things we have to realize about what's going on. This isn't just math. This is very conceptual. So pressure here is what pressure? Yeah, it's 1 atmosphere up here. It's 100,000 pascals. And pressure here is what? Pretty much the same, right? Does the pressure where your feet, so the atmospheric pressure on your feet, can you feel a big difference between atmospheric pressure on your feet and atmospheric pressure at your head? Not a big difference. So since they're effectually the same, and these are all sums, let's just get rid of the pressures. So we've just reduced the terms by 50%. Yay, I have 50% less work to do. We went from 6 terms to 4 terms. Next. Yeah. Okay, since the atmospheric pressure pushing in here and the atmospheric pressure pushing in here is effectually the same, because we're talking about the atmospheric pressure, then those terms are identical. They're 101,000 and 101,000. So we just cancel them out. Since they're sums. If they were products, we couldn't do that. But since they're sums, we can just get rid of them. John?
So the pressure on the bottom has nothing to do with the water?
Oh, absolutely. But the same atmospheric pressure that's pushing down on the fluid is also pushing in on the fluid. The same air we breathe is pushing in every direction.
So if there wasn't the hole, the pressure would be bigger than the water?
Yeah, if there's no hole, there would be no one at number 2 at all. But, yeah. Okay, next. Let's pretend that we set our coordinate system right here, where this is 0 meters. Just like with a ball, if you want to know how much potential energy it has, where do we set the ball? Where do we set the 0 number? On the table. Okay, so we set the 0 number down here. So if we set the 0 altitude where the hole is, what's the height of H2? 0. And if that's 0, do we care about any of the rest of these? Nope. And there it goes. We just reduced another term. We now have 50% of the terms we originally had. Yay! I don't know, still a lot of terms. Here's the next thing we have to realize. The fluid at the top here is going to move a lot slower than the fluid coming out here. Okay? If you take a big drum and you punch a small hole in it, you can definitely see the water coming out, but you're going to wait a long time for that thing to empty. So the velocity here, V1, is much, much smaller than V2. So if it's much, much smaller, guess what we get to do with V1? You get us to cancel it out. And that leaves us with the formula we care about. Rho GH equals 1/2 rho V squared. Mr. Byers, that sounds a lot like PE equals KE. It is. Yeah. So when pressure at depth causes velocity or pressure to move, it looks a lot like PE equals KE. We have to put little triangles in front of things. Which means we have to put a little triangle in front of the H and a little triangle in front of the B. Just like we can put a triangle in front of the BE and a triangle in front of the KE. Yes.
I didn't hear why we crossed out the first 1/2 equals or 1/2 v.
Because this velocity, the velocity of the fluid going down, is so much slower than the velocity coming out. It's effectually 0. So if you imagine a big drum with a tiny hole pumped in the bottom, there's definitely water coming out pretty fast, but that drum's going to take a long time to empty. Exactly. Close enough to 0, we can cancel it out. Is it exactly 0? No, obviously not, but it's close enough to 0, we can cancel it out, and we can reduce our equation to this. And there's one more thing we get to cancel out. Yeah, density. Remember how when we were talking about a ball traveling down a ramp, did the ball lose mass as it went down the ramp? No. So we reduced our potential and kinetic energy to GH equals 1/2 v squared. Similarly, with this, we're going to cancel out our rows, and we're going to get GH equals 1/2 v squared. That's our relationship. And now you have everything you need to know how fast the fluid leaves the hole. G's gravity. G's gravity. I know it's going to come as a shock to you, but G is still gravity.
Oh, G.
Yeah.
Is it cheese?
Oh.
It's gravity. I was like,
Cheese is gravity. Provolone, cheddar.
so confused.
I was so confused. I was like, cheese.
Cheese is gravity.
This
Whoa,
is-
that's profound.
Pro-
That's provolone found. So how fast is the fluid coming out of the hole?
Oh, I didn't know.
6.3 meters per second. Okay. It's the square root of 40.
Yeah.
Okay. Yeah. So 6.3 meters per second.
The pun you guys are making.
Yes.
Monster.
It's 6.3. It's a square root of 40. So basically, when we plug it in, rho goes away, G is 10, H is 2, 1/2 v squared, v is the square root of 2 times 40, or 2 times 20. Okay? Does that make sense? Question?
Can we find out how long it would take for the jump in?
That's the problem, is as it drops, the pressure reduces and the velocity decreases. So this is once again one of those things where we have two equations. We have two variables on either side of an equation sign that are both changing at the same time, and that's the realm of calculus. We could, if we wanted to, find out what it would be at the top and what it would be like halfway, and do a pretty good estimation by using rectangles under a curve. Which, when you take calculus, you'll learn all about rectangles under a curve, but we're not gonna. Yeah. We could, but we're not gonna. Yeah.
So, when you did the formula, you said you got rid of the rows.
Yeah. Because the same fluid that is emptying out of the barrel is the fluid coming out of the barrel at the bottom. So the density is the same on both sides. Does that answer your question?
Yeah.
Okay, next. Now imagine that same barrel with a little brother, actually with a brother, a twin brother, two barrels identical. I have two questions for you. If we punched one hole of one 2-centimeter hole or two 1-centimeter holes, blown up so you can see them, otherwise they'd just be like a pixel. But if we had one 2-centimeter hole and two 1-centimeter holes, which one would empty first, and which one would have the higher flow rate? In other words, which one would have the faster fluid coming out? So why don't you take a minute, chat with your neighbor, which of the two would empty first, and then secondly, which one would have the faster streams of water coming in?
Can I borrow this?
First, I was thinking it's the same. I was thinking it's the same, but because
We're ignoring viscosity.
the stream that
Uh-huh.
Oh, whatever. This is supposed to be times 2.
Yeah. Okay, so I was thinking same. Which stream
So
travels
20
further? That's the. Oh, like out of the water.
So this area is bigger. It's gonna go.
Okay, so the first question, which one empties first? Who says the two holes going to empty first? Who says the one hole is going to empty first? Who says they're the same? They're the same. The pressure that causes the fluid to move is based on just the depth. That's it. Just the depth.
Are those two separate holes, or is that like?
Two holes, yes, two holes right next to each other versus one hole. And then which has a water stream that travels the furthest or travels the fastest? Which one says the one hole has the fastest stream? Which one says the two hole has the fastest stream? Which one says they're the same? Two hole has the fastest stream. Yeah. In fact, if you do the math, two holes equal to the radius, equal in diameter to the radius, will have half the area of this one here.
1.5.
Okay. Anyway, less. So less diameter.
Okay.
Now the last question before we call it a day, or call it a week. The dam break. Imagine there's a river dam that is only 1 meter high. Okay. River dam, 1 meter high, and 3 identical holes end up in the river dam. 1.25 meters below the surface, 1.5 meters below the surface, and 1.75 meters below the surface. Which stream of water will travel the fastest? I'm sorry, travel the furthest. Travel the furthest. So the water's going to go woo, and it's going to go woo, and it's going to go woo. Which stream of water is going to travel the furthest? Yes.
Maybe the bottom one because it has more pressure.
Maybe.
Wait,
Oh,
It has more pressure, but it also is really close to the ground.
Are all
It only has 0.25 meters to fall.
Are they all coming out at the same time, or is it
Yes.
Are the two holes covered and then?
They're all coming out at the same time, and because it's a river, the river is really not dropping really not dropping in depth much at all. It's going to stay 1 meter. So the 0.25 meter only has 0.25 meters of depth, but it has 0.75 meters to fall. The 0.5 meter has 0.5 meters of depth, but it can fall 0.5 meters. And the 0.75 has 0.75 meters of depth, but the water stream is only going to fall 0.25 meters. So why don't you solve that? So you have practice for when you're ready for the test.
So we can do this with math.
No, that's
Please do it with math.
Oh.
Hey, look on the bright side. You're going to get the same question on your test next week.
The exact same numbers.
Exact same numbers. No, they'll be very, very close though. I might only give you 2 holes. In this case, you have 3 holes, so you have 3 different pressures, 3 different velocities, and 3 different distances you're falling. I set it up. I started setting it up right there. Vx1, Vx2, Vx3, dy1, dy2, dy3.
Yeah.
And then when you think you have an answer, we'll go outside and test it if you want. This is my dam. My dam is represented by a PVC pipe with holes at 0.25, 0.5, and 0.75.
I have horrible memory. I wear at least something nice every Friday. At least Mr. Byers notices.
I do notice.
Doesn't matter. You don't notice it, so you don't get any credit. It's still no bother.
Why don't you guys get back on task?
I'm always on task.
Okay, yeah, some of you get back on task. Stop keeping your classmates from learning.
Oh, are we trying to find the, right, but we could find, because this is just how far it would have to fall. But the other one we're trying to find time
Okay.
is how far.
I'm going to turn off the video so we don't spoil it. Otherwise, we're outside anyway, so.